Alright, so Newton's method, as stated here, is meant to find the root of a function using the beginning approximation and a sequential estimation utilizing tangent lines. And the equation as such is up here, and it basically is xn plus 1 equals to xn minus f of x over the derivative of f of x. And an example to simplify that, that's basically just saying x1, let's say, from the beginning, plus 1 is equal to x1 minus f of x over f minus x, and x2 plus 1 is equal to x2 minus f of x over f prime of x, and so on and so forth until you get closer to the exact root of the function, or the x-intercept. And let's go to an example. In order to derive Newton's method shown here, we use the initial tangent to approximate the graph of y equals f of x, where yn is equal to f of xn is small. We then let xn plus 1 be the point where the tangent crosses the x-axis. The culmination of this process is summarized here in this equation for the tangent line. And in order to find this equation, you simply substitute yn equals to the derivative of f of xn and substitute y for 0, then solve for x. Now, to summarize this in a visual process, let's start here. And this would be x0, so the point that you picked or approximated. And you would then, in order to find x of 1, you would draw a tangent line and find where it crosses the x-axis, and that would be x1. And from there, you would use that point to approximate x2 by repeating the same process over again, and that would be x2.
But Professor Cho, doesn't this not work sometimes?
Yes. It doesn't work when, for instance, there are two instances, actually. It doesn't work when the tangent line is horizontal and therefore doesn't intersect with the x-axis. Another time where it doesn't work is where the points of xn increases to infinity, so it increases constantly. For example, this, in which case it will just go continuously on and on until infinity, in which case you would never be able to find the point here.
Oh, okay. Could you show how a problem is done?
Yes. Okay, so this is Newton's method, and this is an example that we put together. This is using the equation y equals x squared minus 2. And you start out with your approximation to get the x0 value. And I put in the value of x equals 1. And so that gives you the y value of the result of 1 squared minus 2, which is 1 minus 2, which equals to negative 1. And that is the y value. That is how I got this right here. And so, in order to find the x1 value, you need to plug that into Newton's method, in which it goes here. And so that would be, that would be negative 1 minus negative 1 squared minus 2 divided by negative 2, which is 2 times negative 1. And so that should give you the value of 1.5 for your x1, and that is right here. So if you draw the tangent line, it should go something like that. And so if you plug that value in, you find where you need to start to find your x2 value. which is stated here. So that's x1 plus 1 equals to 1.5 minus 1.5 squared minus 2 divided by 2 times 1.5. 2 times 1.5, which is 3, if I remember correctly. And if you do this out, you should inevitably get something equivalent to 1.416 repeating, which is right here. Now the actual value of this x-intercept, or this root, is 1.415. No, I'm sorry, yeah, 1.415. So this would grant you a proper estimation of the x-intercept.
Oh, okay. Now I get it. Thank you, Professor Cho.